Hi, I'm Niko Trumbauer, and this is my Simple Harmonic Motion Lab report. So for this lab, my group analyzed simple harmonic motion by testing and evaluating the motion in a swinging spring pendulum. By doing this, we were able to compare the motion in the system to simple harmonic motion in both a spring and pendulum. The objective was to find the equation in the motion in the x and y direction, and compare them to the known equations governing simple harmonic motion. We used the tracker program to compare the motion in the x and the y direction, the x being the motion of the pendulum, and the y being the motion of the spring. So to get the data for this lab, we attached a spring to the pendulum mount and hung a mass of 250 grams at the end of the spring. We then displaced the spring down at an angle to initiate vertical and horizontal displacement of the mass. We then used the video camera to record this, and once we got a good video, we imported that video into Tracker to create position versus time graphs of both vertical and horizontal displacements. So this is a video we recorded using the video camera, and as the pendulum swings and the spring oscillates, Tracker is tracking the motion of the mass, and then it is recording the data on the right of your screen in both the x and the y direction. So once we got the data from Tracker, the next step was to determine the equations of motion for horizontal and vertical displacements. The standard equation for this would be a cosine omega t or a sine omega t, and cosine or sine just depends on whether the graph is starting at a max amplitude, which would be cosine, or whether it's starting at equilibrium, which would be sine. And then A represents the amplitude, and omega represents the angular frequency. So these are the graphs that I got from Tracker after recording my data. And this top graph here is the motion in the x direction, and this bottom graph here is the motion in the y direction. And as you can see, the motion in the y direction, at least the graph, did not come out that well. So I had to use this small section here. This is the only section of the graph that's consistent, but luckily it's enough to where I could get what I needed. And so the first thing I had to do to find my equations for x and y direction was I had to find the amplitude of both. And so amplitude is the displacement from equilibrium. So I found this max value in the max x value at this point, and the minimum x value at this point. And I found the displacement between the 2 points and divided by 2 to find the displacement from equilibrium or amplitude. And I did this for both the graphs. The next thing I had to do was I had to find omega, and omega is equal to 2 pi over the period. So what I did was I found the time value or t value at this maximum point here, and the t value at this maximum point over here. I found the difference between the two, divided by 2 to get the period for one cycle, and then I did 2 pi over that period that I found to get omega, and once again I did this for both graphs. So these two pictures are just showing the work I explained in the previous slide, with the x equation being on the left and the y equation being on the right. For the x equation, I determined that it should be a sine equation because at t equals 0, it is at equilibrium, and I determined that the y equation should be a cosine equation because at t equals 0, the graph is at a maximum amplitude. And so for the amplitudes of both, I found the displacement between a maximum and a minimum point and divided by 2 to get the displacement from equilibrium. And for omega, I did 2 pi over the period that I found. And so my final equation for the x graph would be 0.08 times sine of 5.3 t. And my final equation for the y graph would be 0.02 times cosine of 11.85 t. So once we found the equation for the motion in the x and the y direction of our graphs, we had to compare them to the equations for a spring and a pendulum. The equation for a spring is t of s, or the period, is equal to 2 pi times the square root of m over k, where m is the mass of the spring and k is the spring constant. The equation for a pendulum is t of p, or the period, is equal to 2 pi times the square root of L over g, where L is the length of the pendulum and g is gravity. Finally, it was time to compare our data to what our data should have been in a perfect world. For future reference, our spring mass was equal to 0.25 kilograms, our spring constant was equal to 30 newton meters, our pendulum length was equal to 0.375 meters, and gravity, a constant, was equal to 9.81 meters per second squared. So this is our final data for the actual period versus the calculated period. For the period of the pendulum, we should have gotten 1.228 seconds, but we calculated it to be 1.185 seconds. For the period of the spring, it should have been 0.573 seconds, but we calculated it to be 0.53 seconds. And so after this, we had to calculate the percent error, which is the actual minus the calculated, divided by the average of the two, times 100. And so the percent error of the period for the pendulum was 3.56%, and the percent error for the period of the spring was 7.79%. In conclusion, our spring and pendulum system follows the laws of simple harmonic motion because our calculated period was almost exactly the same when compared to the calculated period when using the simple harmonic motion equations. There are a few factors that could have caused a slight miscalculation, such as the friction between the spring and the pendulum, as the laws of simple harmonic motion do not account for friction, and the tracker program itself. As you saw earlier in our y versus t graph, tracker is not perfect. There could have been an error when tracker was tracking the motion, which would have caused a slight error in calculation. This concludes my simple harmonic motion lab report, and thank you for reviewing my submission.